All right, 10.4 talks about the divergence and integral tests. These are two tests to decide if something diverges or converges. Now, the divergence test tells us that if we know something converges, the summation of it, then the limit as n goes to infinity of the, they're using a k, I'm going to use an nth term, will equal 0. It also says if you take the limit as n goes to infinity of a sub n and you don't get 0, then the series diverges. The thing to be careful of is it doesn't work the other direction. So if you take the limit and you get 0, that does not say anything about whether it converges or diverges. If you don't get 0, it diverges. Now, if you know a series converges, then its limit will equal 0, but it doesn't work necessarily the other direction. So let's look at example 1. They want us to use a divergence test to determine whether the following series diverge or state that the divergence test is inconclusive. So k equals 0 to infinity of k over k plus 1. So if we take the limit as n goes to infinity of, oh I see, now I've got to use a k because the problem has a k. K over k plus 1, that gives me 1. That does not equal 0, so the divergence test can't be used. And the way they wrote it is, the terms of the series do not tend to 0, so this series diverges by the divergence test, because the rule says, oh I said it backwards, if the limit doesn't equal 0, which it doesn't, then it diverges. So let's do part B. We're doing the summation k equals 1 to infinity, 1 plus 3 to the k over 2 to the k. If we look at the limit as k goes to infinity of 1 plus 3 to the k over 2 to the k, we could actually split this up and write it as the limit as k goes to infinity of 1 over 2 to the k plus 3 over 2 to the k. This piece is going to head toward 0. This one, however, is going to head toward infinity. So it doesn't equal 0. So we can say it diverges. And if you have to tell why, then you say by the divergence test. Okay, then part C. Summation k equals 1 to infinity of 1 over k. If we take the limit as k goes to infinity of 1 over k, we get 0. Okay, so the divergence test is inconclusive. And what that means is, as we learn more about the different tests, we would have to use a different test to prove it. Part D, summation as k goes from 1 to infinity of 1 over k squared. Oh, that's going to be the same thing. As k goes to infinity, 1 over k squared is going to go to 0, so divergence test is inconclusive. Next we're going to talk about the harmonic series. Now the harmonic series is part C, 1 over k. And that series is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus ... Question is, does it converge or does it diverge? We can't answer it with a divergence test, so we need a different test. And so the next test we're going to look at would be the integral test, but we need to examine the harmonic series. The way we examine this, you could list out terms all day long. The question is, it could converge or it could diverge. The question is, which one is it? And it's hard to tell. You can keep listing them out. But if you pay attention to what's happening here, those dots, the nth term of this would be 1 over n. And 1 over n conforms to the equation y equals 1 over x. And if you graphed that, the right-hand side of it, because we're only using n's larger than 1, and try to do the Riemann sum on this and try to add them up, and the book used left endpoints on this, you keep drawing them out, left endpoints, and you could say that if I added them all up, that the sum of all those would be larger than the area under the curve. So if I look at the area under the curve and just talk about integrating, and we're going to integrate from 1 to n plus 1, because we're going to go one further than it says, 1 over x dx, that would turn into the natural log, and the plug and chug would be n plus 1. And we know that the natural log function increases without bound. Now, since this function exceeds, since s exceeds it, then s is all of those dots added up. And so that means that if this guy is heading toward infinity, then s sub n would also be heading toward infinity because it's larger. So we're comparing it. So the harmonic series diverges even though the individual terms approach 0. Harmonic series diverges. This also goes back to when we integrated the 1 over n to the p, or x to the p, and we said when p is 1, that'd be my 1 over x, it diverges. Now since we've used the integral to do this, we're going to now use the integral test. The integral test says if you have a continuous positive decreasing function, so integral test, has to be increasing positive, not increasing, continuous, positive and decreasing. Then we can look at the summation. So we have a function f that's continuous, positive, and decreasing. So if we are summing up k equals 1 to infinity, and we look at the function that has the same equation as a sub k, they either both converge or they both diverge. What it means is if I work out the integral and I get an answer, that means it converges, so that the summation also converges. And in general, it's equal to the value of the series. Is not in general equal to the value of the series. You can't just say I integrated it, my answer was 5, so the summation is 5. It doesn't work that way. It just tells you whether it converges or diverges. So I'm reading it out of the book. They either both converge or both diverge. In the case of convergence, the value of the integral is not, in general, equal to the value of the series. But if you do the integral and you get infinity or negative infinity, then you know the series diverged. So it doesn't help you find the sum, but it does help you decide whether it converges or diverges.